studying in Diploma in Medical Imaging. My group members are Ellen Batusha binti Arif, Nainin Nur Husna binti Hasbullah, Nur Husnina binti Hasin Nur Nizam, Nuri Fariza Hilma binti Muhammad Faizal, Nurul Haswani binti Mat Hassan, and myself. And we will be working together in this assignment. So I'm going to let you know all of the things that inside the X-ray room. So this one is the control panel. First, this is the X-ray view. This one is the collimator. Collimate. This one is the table. This one is the bar key. This one is the generator. The journey from the panel to the image starts at the control panel, where exposure factors are selected. X-rays are then produced in the tube, passed through the patient, and are captured by the image receptor to form a diagnostic image. Important for interdisciplinary collaboration, understanding this process is important not only for radiographers but also for other healthcare professionals. For example, a pharmacist who understands radiation principles can better ensure patient safety, especially when medication interact with imaging procedures or contrast agents. A physiotherapist who understands imaging can accurately interpret radiological findings, helping to plan appropriate rehabilitation and treatment strategies. This shared knowledge improves communication, reduces errors, and enhances patient-centered care. In conclusion, knowing how an image is produced from the control panel to the final image strengthens teamwork across healthcare disciplines. When professionals understand each other's roles and technologies, it leads to safer practice, better diagnosis, and improved patient outcome. Thank you.
Assalamualaikum and hi. Very good morning to everyone. My name is Nur Husnina binti Hasironiza, and today I will explain to you about control panel. What is control panel? Control panel is considered as the brain of X-ray machine. Why is that happen? It is because control panel is to control the exposure and used by the radiographer before taking an X-ray image. This is the control panel. It determines how strong the X-ray beam, how many X-rays are produced, and how long the exposure lasts. Incorrect settings here can lead to overexposed image, underexposed image, or unnecessary radiation to the patient. This is the KVP control. KVP means kilo voltage peak. KVP controls the energy and penetrating power of the X-ray beam. When KVP is increased, there will be more penetration, image contrast will be lower, and there will be more shades of gray. KVP also determines the speed and kinetic energy of electrons. It means that when higher KVP are given, the electrons that strike the anode are with the greater energy. For example, for chest X-ray, we need a higher KVP. Next is MA. MA stands for milliamperes. It controls the number of electrons that flowing from the cathode to the anode. For easy to understand, MA controls the amount of current flowing to the X-ray tube's filament. The higher the MA, the more electrons are heated and released from the filament, and this results in more X-ray photons being produced. So basically, MA affects the quantity or intensity of the X-ray beam. Next is MAS. MAS, which is the product of MA and exposure times in second. It means that it controls how long the electron flows. It represents the total amount of radiation used to create the image. Increasing MAS will increase the image density, which makes the image darker. It will also increase the radiation dose to the patient. For example, 200 mA for 1.0 seconds give us 20 MAS. You can increase or decrease MA or time, but what matters most is the final MAS because that determines image density. On the control panel, you can either adjust MA and MAS separately or sometimes just set the desired MAS directly. That makes the process more efficient, especially with digital systems. It is important to choose the correct MAS based on the patient size and the body part that being imaged. If MAS is too low, the image may be underexposed or appear too light. If it is too high, it is not only overexpose the image, but also increase the patient radiation dose, which unnecessarily. In summary, MA and MAS play a big role in achieving the right image quality while keeping patient exposure as low as reasonably achievable. This is the part of examination. It has such as skull, chest, abdomen, spine, pelvis, upper extremities, and also lower extremities. Then, lower part of examination, we have chest projection. There is chest PA, chest lateral, chest oblique, and many of them. This is dose display. It displays a dose that delivered to the patient when we do examination. Then we have patient body size. We can choose body size of the patient. This is for kids, a small patient, normal size, and a bigger size of body patient. This is green. We use this for abdomen. See, in auto setting. This is the exposure button. The exposure button is the control that allows us to set the X-ray exposure. It usually a two-step button, meaning it has two stages when pressed. In the first stage, when we press halfway, it activates the rotor. This starts the anode rotation and begins heating the filament. In the second stage, when we press fully, it actually starts the X-ray exposure, allowing the current to flow and X-ray to be produced. It's important to press the button in one smooth motion and hold it until the exposure is complete to avoid errors or incomplete exposures. Usually, when you press the exposure button, you need to wait until the green light shows before you press it hardly. The design of the exposure buttons also follow radiation safety principle. It is often placed outside the X-ray room, behind a protective barrier, or attached to a long cord for mobile X-ray. It allows the radiographer to stand at a safe distance. All the settings on the control panel are interconnected and must be selected together, not individually. The two most important exposure factors are KVP and MLS, and each one affects the image in a different way. KVP controls the quality and penetration of the X-ray beam, while MAS controls the quality of X-ray produced. In conclusion, the control panels allow the radiographer to control KVP, MA, and MAS, which directly influence image contrast, image density, and patient radiation dose. Proper use of the control panel ensures diagnostic image quality while adhering to radiation safety principle. That's all from me. Thank you.
Hi everyone, my name is Nurdin Farizah Hilma binti Muhammad Faizal. My ID number is 59106324328. Now that we have shown you the control panel where the exposure settings are made, let's look at where the magic actually happened. This is an X-ray tube, the component that is responsible to generate X-ray beam that travel through the patient to create an image. Inside this protective housing is a vacuum. There is two main components inside this tube, which is cathode and anode. Cathode is a negative electron. It contains filament that when heated will release electron. These electrons then shoot at high speed toward the anode. Since cathode is the component that shoots negative electron, then anode is the component that receives it. Anode is a disc usually made out of tungsten since it has high melting point and high atomic number. This helps in efficient X-ray production.
In this diagram, you can see how an X-ray tube works. The tungsten filament of cathode is heated up by electric current that release electron by thermionic emission. These electrons form an electric beam. This beam travels in a straight line across the vacuum, which then directed toward the anode. The electron beam then strikes the heavy metal target on the anode, which is made of tungsten. When the high-speed electrons interact with the tungsten target, their kinetic energy is converted into heat and a small amount of X-ray photons. These X-rays are produced at the focal spot of the anode. A high-tension voltage, EHT, is applied across the cathode and anode to accelerate the electrons. The entire tube is enclosed in a vacuum. This allows electrons to travel freely without colliding into air molecules. The X-ray beam generated at the anode then exits the tube through the tube window and travels towards the patient or image detector. This process shows how the cathode produces electrons, the anode converts electron energy into X-rays, and the vacuum and high voltage enable efficient X-ray production.
In order to get a high-quality image, we must look at these few specifications. First is focal spot size. Imagine this as the tip of the beam. A smaller focal spot will result in a much sharper image with better detail, while the larger one will handle more heat for fast and thick anatomy image. Second is anode angle. This angle helps us maintain a large area for heat to heat while keeping the effective focal spot small for better resolution. Third is tube rating. This is essentially the safety limit of the tube. We must ensure our setting don't overheat the component, ensuring the equipment to last long. By understanding these internal mechanics, we can choose the right setting to achieve clear diagnostic image while keeping the equipment safe. That's all from me. Now, I'll pass to my friend who will explain about the powerhouse of the whole process, the generator.
Hello, my name is Nur Hassan. I will explain about the powerhouse of the X-ray system, which is X-ray generator. So, let me tell you the role of generator. The main role of generator is to provide high voltage to the X-ray tube. This high voltage is necessary to accelerate electron from cathode to anode inside the X-ray tube. When the electron side anode with high energy, X-rays are produced. Therefore, the generator is essential for the production of X-ray. Besides that, the generator helps to control the electrical supply and consistent X-ray output. There are a few types of generator. The first one is single-phase generator, which are usually found in older or basic X-ray systems. Secondly, we have a three-phase generator, which provide more continuous and efficient X-ray output compared to single-phase. Lastly, we have high-voltage generator, which most commonly used in modern X-ray machine. High-frequency generator is preferred because they produce better exposure factors controlled by generator is KBP. When the radiographer selects a KBP value on the control panel, the generator supply a corresponding high voltage to the X-ray tube. The selected KBP affects the energy and penetrating power of the X-ray beam, which will increase image contrast and patient dose. Therefore, the generator plays a key role in converting the exposure setting into actual electrical output.
Alright, so let's move on to the components of generator. The X-ray generator consists of several main components that work together to produce X-ray safely and efficiently. First, we have autotransformer. This allows us to select the desired KVP by adjusting the voltage. Next is the high voltage transformer. Its role is to increase the voltage to a very high level, enabling electrons to move from cathode to anode. Moreover, the filament or step-down transformer, supplying low voltage and high current to heat the filaments, which releases electrons. Furthermore, the rectifier then converting alternating current into direct current, ensuring that electrons flow in one direction only. Finally, the control panel is where the radiographer selects the KVP, MNS, and exposure time. Like all these components work together to ensure a stable and safe X-ray exposure. By accurately controlling exposure factors, the X-ray generator helps use only the necessary amount of radiation, supporting the LRR principle. Now, let's discuss the X-ray generator waveforms based on the diagram shown here. First, let us look at the half-wave rectification, which is shown on the left side of the picture. In half-wave rectification, only the positive half of the alternating current is used to produce X-rays, while the negative half is blocked. Because of this, X-rays are only produced during half of the electrical cycle. This type of rectification can also be called self-rectification, and it usually uses 0 or 3 diodes. Since we are using 60 Hz power supply, half-wave rectification produces 60 pulses per second. Because X-ray production happens only half of the time, the efficiency is low, and we need a higher exposure technique, meaning higher MAS, to get adequate image quality. This type of generator is usually found in older or portable X-ray machine. Next, let us move to the full wave rectification, which is shown on the right side of the diagram. In full wave rectification, both the positive and negative halves of the AC waveform are converted into positive voltage. This means X-rays are produced continuously without long gaps. Full wave rectification uses 4 or more diodes, commonly arranged in a bridge circuit. With a 60 Hz power supply, full wave rectification produces 120 pulses per second, which is double compared to half wave rectification. Because the output is more constant, it is more efficient, and it requires about half the exposure technique compared to half wave rectification. In conclusion, half wave rectification produces fewer pulses and is less efficient, while full wave rectification produces more pulses, provides smoother X-ray output, and results in better image quality with lower patient dose. This is why most modern X-ray machines use full wave rectification.
So, in summary, the X-ray generator acts as the powerhouse of the system. It provides high voltage to the X-ray tube and responds to the exposure setting selected in the control panel. So, without X-ray generator, the X-ray system cannot function effectively. Thank you.
Assalamualaikum and hi, my name is Nabila Husna Fitriasmila. Today I will explain about the anode effect, which describes how the X-ray beam intensity varies across the field and its importance in clinical radiography. What is anode effect? Hill effect is a phenomenon where the X-ray beam intensity is higher at the cathode side and lower at the anode side of the X-ray tube. This means the X-ray beam is not evenly distributed across the image receptor. There are three factors affecting the anode hill effect, which are the anode angle, the field size, and the source to image distance, also known as SID.
The first and most important factor affecting the anode hill effect is the anode angle. As we all know, in an X-ray tube, the anode is angled rather than flat. The anode angle increases the surface area of the focus point, which increases ability of anode to absorb heat. This anode angle is important because it helps reduce the effective focal spot size. However, this angulation also causes the anode hill effect. X-rays produced on the anode side must pass through a greater thickness of the anode material before exiting the tube. As a result, more X-ray photons are absorbed within the anode, causing lower beam intensity on the anode side. Meanwhile, X-rays produced on the cathode side travel through a shorter distance of the anode material. Therefore, less absorption occurs, resulting in higher beam intensity on the cathode side. The smaller the anode angle, the more the anode hill effect becomes. The second factor affecting the anode hill effect is the field size. When a small field size is used, the difference in beam intensity between the anode side and cathode side is minimal and may not be noticeable. However, when a large field size is selected, more of the anode and cathode sides are included in the X-ray beam. So, this causes the difference in beam intensity to become more obvious, with the cathode side receiving a higher intensity beam and the anode side receiving a lower intensity beam. Therefore, the anode hill effect is more pronounced with larger field sizes. The third factor influencing the anode hill effect is the source to image distance, also known as SID. When a short SID is used, the X-ray beam diverges more rapidly. This increases the difference in beam intensity between the anode side and cathode side. As a result, the anode hill effect becomes more noticeable at shorter SID. On the other hand, when a longer SID is used, the beam divergence is reduced. This makes the intensity difference across the field more uniform. Therefore, the anode hill effect is less noticeable at longer SID. Besides that, the anode hill effect can be used to our advantage by placing the thinnest portion of the patient under the anode side of the beam and the thickest part of the patient under the cathode side. For example, when imaging a foot X-ray, the toes should be positioned toward the anode and the ankle toward the cathode. As for the abdomen X-ray, the cathode is positioned towards the superior abdomen, which is the thicker part of the body, and anode towards the pelvis.
In summary, the three factors affecting the anode hill effect are the anode angle, field size, and source to image distance. The smaller anode angle, the larger field size, and the shortest SID will increase the anode hill effect. Understanding this effect helps the radiographer optimize image quality and apply correct patient positioning. That's all from me, Naila Musnah. Thank you.
So we have now touched on the main things like the control panels, which is where radiographers controls KV and MAS, along with what symbol and icon does, and how does changing KV and MAS affect the quality of an image. And then we've touched on the X-ray tubes, functions of the components inside the X-ray tube, like the cathode and anode, along with how the design of X-ray tube component, like the focus spot size, will affect the image. And then, moving on to the generator, we've touched on the functions and the types of the generator that is used on X-ray machines. And then, after that, we focus on one of the core principles, which is the anode hill effect, that basically explains how the angle of anode affects the focus spot, which then will have an impact on the sharpness of the image. I think we can all agree that those things are essential to know when you are a staff working in the radiography field. We can also agree that those things are the fundamentals of general radiography machine, and without those components, we wouldn't be able to capture X-ray images and help doctors make an accurate diagnosis. However, as a radiographer, you all will encounter many types of machines that has those main components but will still produce a different result of image, even when you use the exact textbook accurate amount of exposure and the exposure time. Now, this is a very common thing to experience, and allow me to tell you why this happens. First and the most obvious reason is the types of system that is used, which is either the computer radiography system or the digital radiography system. We know that the DR system has a more advanced technology in producing a high quality and a better contrast image because of its efficiency of converting the X-rays into electrical signals compared to CR system. The R system also has a tolerance in maintaining the quality of an image even when it is exposed to a lower exposure compared to CR system. But aside from that, the manufacturer of the machine is one of the factors affecting the image quality. This is because of the different system calibration and the protocols that the manufacturer might do for these machines. So, let me briefly explain about system calibration. The system calibration is processed by the manufacturer, or in some cases, a medical physicist, to ensure that the X-ray output, like the KVP, MA, and time, is accurate, the response of the detector and the automatic exposure control matches the X-ray exposure, the exposure index matches the detector dose, and the image processing software response well at different exposures. Then, manufacturers will follow a default exam protocols. So what will happen is the manufacturer enters a few standard X-ray examination like chest, abdomen, and extremities to load the default of each KVP, MAS, AEC selection, and target exposure index as a standard for that machine. So, this is why certain machines has different default settings to produce a good quality image, and why we can apply the same amount of exposure even when the machine has the same type of system like the other machine. Some manufacturers prioritize low noise image when using the standard amount of exposure. Some prioritize using low amount of exposure dose to the patient while producing a high quality image. But even then, there must be a law and regulation for all X-ray machines, and even the staff working in the radiology field. The X-ray machine must be monitored in terms of mechanical aspects, such as the light beam alignment and the equipment stability. Then in terms of radiation and electrical safety aspect, such as the tube filtration and tube leakage. And then the X-ray beam aspect, which is the focus spot size, tube output, and the exposure time. This is what we call the quality assurance test that will be done by a medical physicist or a quality assurance committee or an engineer. And then for the staff working, rules have provided that radiographers must wear an optical stimulated luminescence, also known as OSL, which is a device that is used to monitor the amount of radiation on a person, which radiographers has an effective dose limit of 20 millisievert every year. Aside from that, radiographers have been provided with a bunch of protective equipment, for example like the lead gown for all staff during angiography, and using lead shield to shield other staff during mobile x-rays to reduce their effective dose limit. In conclusion, technology has come so far in helping the human to cure diseases. Understanding how every component of the X-ray machine, from the generator to the X-ray tube to the cassette and the ear-bucky, holds a big purpose in the medical field. X-rays can help a doctor in diagnosing a minor condition to chronic long-term disease. it can help a physiotherapist determine the severity of musculoskeletal injuries down to the joint problems in patient. X-rays can also help dentists plan surgeries for teeth and jaws, and even do braces planning with patients. However, just like the saying, with great risk comes great rewards. X-rays is one of the first procedure in determining an illness, but it also can be dangerous when X-ray machines are not properly maintained and exposures are not properly controlled. Being educated about this knowledge is essential not only for operating the equipment effectively, but also for ensuring safe and ethical practice in medical imaging. So that will be all for this video. Thank you for listening.